numbers here. And if player 1 chooses B, player 2 also plays a normal form game. Okay? And this game and this game, they can be different games. Okay? And of course, let's say outcome of these games affect player 1's payoff. Okay? Then, in order to maximize profit of player 1 has to make some prediction about what's the outcome of this game and what's the outcome of this game if they are actually played. Okay? And then, given that all players are rational, and that is common knowledge, and all players have rational expectation, then player 1 has to believe that if he chooses A, then P2 and P3, player 2 and player 3, they have to play a Nash equilibrium in this sub-game. Okay? And if player 1 chooses B, then player 1 has to believe if she chooses B, then player 2 and player 3 has to play a Nash equilibrium for this sub-game, in this sub-game. Okay? And let's say player 1's payoff in this sub-game, in this Nash equilibrium is 3, and let's say player 1's payoff in this Nash equilibrium is 4, then player 1 has to choose B. Okay? So you can see exactly the same idea is applied here. Player 1 have to make some prediction about the future. Where if he chooses C, then the reasonable prediction is, I don't know, but okay, so I'm sorry. So maybe the reasonable prediction is player 2 has to play a Nash equilibrium strategy. And if player 2 has to make prediction about this sub-game, then we have to, player 2 has to believe that at least they have to play a Nash equilibrium in this sub-game. Like player 1 has to believe player 2 and player 3 have to play Nash equilibrium in this sub-game. Okay? Okay, and the idea of sub-game perfect equilibrium also reflects our initial idea that player 1 has to take into account that his or her action will change future play of other players. Right? So for example here, player 1 will, if player 1 chooses A, then they will play Nash equilibrium here. And if player 1 chooses B, then they will play Nash equilibrium here. And by thinking that way, player 1 really takes into account the effect of his move onto the future player. Future play of player 2 and player 3. Okay? Okay, any question? I mean, I kind of teach this game theory course every year, and what I know based on my experience is this is kind of the first moment that many of you begin to have some difficulty following the lecture. So this is kind of really subtle and really complicated stuff. So I mean it's totally okay. I mean if you have some difficulty here, I mean it's totally natural. Just as some questions. If you have anything unclear, and by answering that question, then you will understand everything more clearly. or maybe another reason that if you have any difficulty, another reason for that is maybe it's just the first lecture after the break. Yeah. So every year I find that it's very difficult in the lecture just after the break. So yeah, I'm not really sure whether break is really good for in terms of teaching and about education. So I'm not really sure, but anyway. So okay, and if you think about the procedure we did here is soft-gain perfect equilibrium is always, you can always solve for soft-gain perfect equilibrium by backward induction, right? So you have by backward induction. The backward induction asks what is best response of player 2 if this node is reached, right? So backward induction beginning what is player 2's best response at the very end of the game. And answer for that question is, okay, player 2's best response, optimal decision has to be S. That is exactly equivalent to asking what is Nash equilibrium for this subgame. And answer is again S here, right? And then backward induction requires that given this choice as fixed, now you ask what is the best response of player 1 in this node, right? And the answer is this one, S, because by choosing S, player 1's payoff will be 5, but if player 1 chooses C, then payoff will be 4. So 5 is better than 4, so player 1's best response here is S, right? And that is exactly equivalent to asking what is Nash equilibrium for this subgame, right? And answer is again, Nash equilibrium has to specify S here. Okay? So in this example, you can see actually subgame perfect equilibrium. The idea of subgame perfect equilibrium is exactly identical to the idea of backward induction. So actually that is true for any finite extensive-form game. So whenever you have finite extensive-form game with perfect information, you can solve for subgame perfect equilibrium by backward induction. Okay? Okay, so I have a couple of more examples on the slide. So we already did this example together. This example, this slide is asking, to find out all subgame perfect equilibria by backward induction. So there are two subgames, and we already know that player 1's action has to be F in the second subgame, in the small subgame here, right? Otherwise, it fails to be a Nash equilibrium for this subgame. And given that player 2 has to choose O, otherwise it fails to Nash equilibrium for the entire game. So this game has unique subgame perfect equilibrium in which player 1 chooses F and player 2 chooses in. I'm sorry. Player 1 chooses. Sorry. I was wrong. Okay. So you have to tell me actually, if I do everything wrong. Okay, so there is unique subgame perfect equilibrium such that player 1 chooses A here and player 2 chooses I here. Okay? What about this game? So this game is actually also, I'm kind of, already kind of solved this game, but so actually this game also has unique subgame perfect equilibrium, and you can solve that unique subgame perfect equilibrium by backward induction. Basically, player 2 has to choose S. Actually all players choose S in this unique subgame perfect equilibrium. Okay, you can solve that unique subgame perfect equilibrium by backward induction. Let's read it. Okay, so what about what about this game? So this is something we didn't really try. We have not tried this game yet. Okay, so let's solve this game together. Let's solve for subgame perfect equilibrium for this game together. Okay, so first of all, this game has infinitely many subgames, right? Whenever player 1 chooses a number S1, then there is a subgame such that player 1 has to choose, player 2 has to choose either yes or no. Okay? And player 1 can choose any number between 0 and 1, so which means that there are infinitely many subgames. Okay? Okay, so okay, so let's say player 1 chooses any number between 0 and 1, then we have subgame like this, right? And let's ask what is Nash equilibrium for this subgame. Okay? Then in this subgame, there are two cases, actually three cases. Let's say, two cases. Let's say S1 is less than 1. Okay? So price, okay, so remember that our interpretation of this game is player 1 is seller and player 2 is buyer, right? So buyer think the value of the good is equal to 1, and S1 is price offered by the seller. Okay? So as long as, okay, so let's look at the case where S1 is strictly less than 1. So price is less than 1. First of all, if buyer says no in that subgame, then payoff is 0 for player 2, right? If player 2 chooses no, then there's no deal, so payoff for player 2 is 0. Okay? However, if player 2 chooses yes, then there is a deal, so they trade the good at price equal to S1, which is less than 1. So buyer's payoff is 1 minus S1, right? Which is positive, as long as S1 is strictly less than 1. Okay? So which means that as long as S1 is strictly less than 1, the buyer's best response has to be yes. Okay? In other words, as long as in any subgame following S1 strictly less than 1, there is only one Nash equilibrium for that subgame. And in that unique Nash equilibrium, player 2 has to choose yes. Okay? So in this case, the subgame has a unique Nash equilibrium, and player 2 chooses yes in that unique Nash equilibrium. Okay? So if S1 is strictly less than 1, the subgame has a unique Nash equilibrium, and in that unique Nash equilibrium, player 2 chooses Y. Yes. Okay? And that means the payoff will be S1 and 1 minus S1. Okay, S1 for player 1, the seller, and 1 minus S1 for player 2, the buyer, right? Player 2 chooses yes, so they trade a good, and the seller's payoff is just revenue, S1, the price equal to the price he offered, and the buyer's payoff is 1 minus S1, where S1 is the buyer's value of the good, and S1 is what the buyer has to pay. Okay? Okay, so case 2. What if player 1 chooses 1? So price is exactly equal to 1. So then you can see the player 2, the buyer, is just indifferent between two actions. If player 2 chooses no, then again there's no deal, so payoff for player 2 will be 0. If player 2 chooses yes, then they trade a good, but price is exactly equal to the value of the good. So the buyer's final payoff will be 0. 1 minus 1, which is equal to 0. So the buyer's payoff will be 0, independent of his or her decision in the subgame. Two actions result in exactly the same payoff for the buyer. Okay? So the buyer is just indifferent between yes and no. So in principle, that means the player 2 can randomize, right? Player 2 is indifferent between yes and no, so the resulting payoff will be exactly the same. So any randomization over yes and no would be a best response for the buyer. Okay? So any behavior strategy of P2 is her best response. Okay? If P2 chooses yes with probability, let's say P. Okay, so any randomization is best response. So, and which means that any P will be a best response, right? Then, if this is the strategy, then P1's expected payoff from choosing S1 is what? So with probability P, player 2 will choose yes. Okay? And in that case, what is the seller player 1's payoff? It will be 1, right? So S1 is the price offered by the seller in that case. And if player 2 chooses yes, then seller's payoff will be 1. And if player 2 says no, then the seller's payoff, the player 1's payoff will be 0. So anticipating that, player 1 has to think that if I choose S1, given that player 2 will choose yes with probability P, my expected payoff will be P. With probability P, my payoff will be 1. With probability 1 minus P, my payoff will be 0. So expected payoff is simply P times 1, which is P. Okay? Is it clear? Everything so far? Okay? So let me briefly repeat what I have done here. Okay, so if player 1 chooses S1 equal to 1, then player 2 is just indifferent, right? Just indifferent between yes and no. Because in any cases, player 2's payoff will be 0. Okay? Which means that, okay, so my payoff does not depend on my action in player 2's perspective. That means any randomization over y and n is a best response for player 2, right? Because, I mean, actually, because my payoff is always 0 for any randomization I can do. Okay? So in equilibrium, anyway, so player 2 has to choose one P, right? And if P is fixed, then you can calculate what is player 1's expected payoff from choosing S1, equal to 1. That will be equal to P. Okay? Because with probability P, the seller's revenue will be 1. And with probability 1 minus P, my revenue, the seller's revenue is 0. So expected revenue or expected payoff is exactly equal to P. It's the analysis for all subgames after the one's choice of S1. And given that, now we have to think about what is player's best response. In equilibrium, player 1 has to choose S1 that reserve the payoff. Okay? Okay, so let's first look at the case where let's suppose P is equal to 1. Okay? So let's check whether it is subgame property equilibrium. Let's say here we are asking if there is any subgame property equilibrium such that player 2 chooses yes with probability 1 if S1 is equal to 1. Okay? Okay, then if player 2 chooses yes here with probability 1, then what is player 1's expected payoff? So here I draw S1 on the horizontal axis and U1 player 1's payoff on the vertical axis. So here we have 1. So as long as S1 is strictly less than 1, then the seller, the player 1, knows that player 2 will say yes. Okay? So my payoff will be equal to S1. So graphically, that means the graph of my U1 is like this. Okay? And if S1 is 1, then actually, it is also on the line here. Provided that player 2 will accept S1 with probability 1. Okay? Then clearly, in player 1's perspective, it is best response to choose S1 equal to 1. Okay? So we just find out one subgame perfect equilibrium. In that subgame perfect equilibrium, player 1 chooses S1 equal to 1. Okay? And player 2 chooses yes for any offer, for any S1. Okay? So player 1, so in this subgame perfect equilibrium, player 1 chooses S1 equal to 1. So that's the strategy, equilibrium strategy of player 1, right? And we also have to specify what is equilibrium strategy of player 2, right? And equilibrium strategy of player 2 is yes for any S1. Okay? So here, what you have to be conscious here is, we have to specify what player 2 will say for any S1. Right? Because when I say because otherwise in equilibrium we have to specify strategy of all players, right? And in particular, each player's strategy has to specify what is randomization I'm gonna do for any possible situations. And in that, when I say any possible situations, I have to include all cases, including the situation which is never happening in equilibrium, right? Strategy has to give a complete plan for all possible, contingencies, right? So which means that player 2's strategies has to say either yes or no, or any randomization between yes and no for any possible S1, right? So whenever I ask what is equilibrium strategy in subgame perfect equilibrium, you have to specify what player 2 will do after any S1. Okay? So anyway, coming back to our conclusion here, it is subgame perfect equilibrium such that player 2 always says yes, and player 1 chooses S1 equal to 1. S1 equal to 1 is best response. You can see that from the graph on the board. And player 2's strategies is also best response because as long as S1 is strictly smaller than 1, player 2's best response is clearly saying yes, right? And if S1 is exactly equal to 1, player 2 is actually independent, but of course, then saying yes is also a best response. Okay? Okay, then what if P is less than 1? If P is less than 1, then we have to change this graph a little bit. So remember that here, if P is, the expected payoff from choosing S1 equal to 1 is P for player 1, right? So if P is less than 1, which means that if player 2 is choosing yes, in this case with probability less than 1, then this graph will look like this. Right? Okay, then what is best response of player 1? The answer is actually there is no best response of player 1. Right? Just give me, any, for example, just give me any number between 0 and 1. Let's say, you give me 0.9. Okay, so let's look at whether there is the 0.9 is best response of player 1. Clearly, that is not best response because if player 1 chooses 0.9, then my payoff, player 1's payoff will be 0.9. But player 1 always can deviate slightly higher price. Let's say 0.95 is better strategy. Okay? What about 0.99? That is still not the best response of player 1. 0.999 can be better than 0.99. Okay? So, which means this is a little bit subtle. So, which means, so as long as P is strictly less than 1, player 1 has no best response. right? But in equilibrium, every players have to play a best response, right? In every equilibrium, every players have to choose a best response. But in this case, if player 2 chooses P less than 1, then player 1 has no best response. Okay? Which means that there is no way for player 1 to choose a best response. Okay? So here, the conclusion here is, so this is the subtle part. Then we have to conclude that there is no subgame perfect equilibrium such that P is less than 1. Okay? This is subtle part, definitely. Let me repeat one more time. In Nash equilibrium, or any kind of equilibrium actually, every players have to choose their best responses, right? That is clearly, okay, so in so especially, let's focus on subgame perfect equilibrium. In subgame perfect equilibrium, every players have to choose best response in any subgame, right? In other words, every subgame, every players have to play Nash equilibrium for any subgame. So that means every players have to choose best response for any subgame, in any subgames, right? But if P is less than 1, then player 1 has no best response. Because for any strategy, it is always better for player 2 to increase price a little bit more, right? So player 1 has no best response, which means that there is no equilibrium such that P is strictly less than 1. Whenever P is strictly less than 1, player 1 is always, there is always room for improvement for player 1. Okay? So let me put it this way. So in equilibrium, everyone has no incentive to move further. Everyone has no incentive no reason to change their mind. But that is impossible whenever P is less than 1. Okay? So by doing that, in conclusion, there is a unique subgame perfect equilibrium for this game, right? Such that P is equal to 1. Okay, so any questions so far? Okay, so summing up, today we have discussed subgame perfect equilibrium, which is the solution we're gonna use whenever we talk about extensive form game with perfect information. Okay, and the definition of subgame perfect equilibrium is that so a strategy profile is subgame perfect equilibrium if it is a Nash equilibrium in any subgames. Okay, so the idea of subgame perfect equilibrium is basically there are two things, actually two ideas. First, whenever a player makes a decision, that player has to think about what is the future player's decision in the game, sub-game following my decision, right? Then remember, then it is reasonable to assume that that player will believe future players will play, at least they play a Nash equilibrium, right? So that idea was most clearly understood in the game I drew previously on the board. The game that player 1 chooses A and B first, and then player 2 will play a sub game for each case, right? So and these sub games are normal form games. Then it is reasonable that player 2 will believe whenever I choose a decision, the other players 2 and 3, they will play a Nash equilibrium for that sub game. Okay, so in that sense, like in that example, it is actually very reasonable to say that all players will believe the future players will play a Nash equilibrium in any possible sub games. Okay, so that's the idea of sub game perfect equilibrium. Okay, any reasonable outcome has to be based on all players' expectation that future players will play Nash equilibrium. Okay, and that notion of sub-game perfect equilibrium also reflects our very initial observation that a player has to take into account what is effect of my decision on the future players' actions, decisions in the future. Okay. So definitely sub-game perfect equilibrium is kind of difficult concept. It's actually really deep concept actually. So maybe it takes some time for you to digest it. I mean, maybe some examples will be helpful, which I will give you later, as a form of in the second problem set basically. Okay, so that's the thing. The first thing we discussed about sub-game perfect equilibrium and what is the idea behind it, and also we discussed what is the procedure to solve for sub-game perfect equilibrium. Actually, the idea of sub-game perfect equilibrium is almost identical to the idea of backward induction, which we discussed at some point of time today. And indeed, for any finite, and actually not only finite, but almost not all actually, but actually for many for many extensive form games, you can actually solve for sub-game perfect equilibrium using backward induction. Okay, and one example we did is still written on the board, remains on the board. So for ultimatum bargaining game, in order to solve sub-game perfect equilibrium for ultimatum bargaining game, we first asked what is player 2's best response after any S1, right? Or equivalent to speaking, we asked that what is Nash equilibrium for each sub-game after any S1. And then we move backward, right? Given our answer to these questions, we move backward and ask that what is best response of player 1. Okay, so that's the procedure we can solve for sub-game perfect equilibrium. And in this particular example of the ultimatum bargaining game, there is a unique sub-game perfect equilibrium, such that player 2 always says yes, and player 1 chooses S1 equal to 1. And one separate thing was there is no sub-game perfect equilibrium such that P on the board here is strictly less than 1. Because in the equilibrium, everyone has to play best response, but we just found that if P is strictly less than 1, player 1 has no best response. So which means that there is no sub-game perfect equilibrium such that player 2 chooses yes with probability less than 1 after S1 is equal to 1. Yeah. Okay, so there are a couple of other things I have to explain a little bit more on the slide. So, but I'm gonna do that next week. So here, for example, there's some discussion about sequential rationality. So I'm gonna discuss that part next week. And also I'm gonna discuss the slide about one-shot deviation principle also next week. Okay? There is also an announcement